Okay, let's begin. Just quick reminder that tonight is the Harvey Meyer picnic thingy-mabob. I don't know what they call it. They got some goofy name. Harvey's Hoedown. Harvest. Okay. Anyway, looking out of the sky, I'm pretty sure it's going to be in the atrium here beside the Woods Auditorium, right? They said they would keep us updated, but I don't see how that sky is going to allow for much outdoor activity. So hopefully you enjoy that. Hopefully you enjoyed yesterday helping people out. I certainly enjoyed getting some more grading done because I was helping you guys out, well, helping me out and teaching. I do have the next homework assignment available to you to see the next homework site here. That's not it. It should have been when I clicked there. Cruise down here, and it's now in section part 2. So there's homework 3, and you can look over the questions. I'm not going to answer the questions here, but just point out that they are there, so you can get started. We clearly haven't covered all of those things yet, right? We've only had one lecture so far on those. Now that reminds me, the last homework assignment, I completely forgot to cover tides, and you had a homework question on it. So I was really generous. Like the lowest score I gave on that was an 8 out of 10 because I figured it hasn't been lectured on, and I know it's within the realm of theory for a class to have people look things up and learn on their own. I like to, at least have gone over it. So I'll go 3 quick slides and 1 animation. But before even that, I like this. I went to log into my computer this morning, and that was the lock screen. I was really impressed. And so you guys, I hope, are equally impressed. What do you see there? What thoughts come to your mind just from looking at that picture?
Rainbow.
Okay, he said a rainbow. It's not a rainbow, but I said thoughts. I didn't say what is it, so it's a fair thought.
It almost looks like there were like fires in the distance.
Okay, it looks like fires in the distance. It's also not fires, but that's what it looks like. And those are actually the 2 things that stood out to me that I wanted to bring out from this picture. The 2 things are, number 1, obviously this is a wide angle. This here, it's not a rainbow. That's the Milky Way. It's called the Milky Way because it kind of looks like a road of milk. One of the names for the Milky Way in ancient language was Via Galactica, the way of the milk. Or Galactica is milk in Greek. And then in Latin, there's something else, Latin. I don't know. I didn't look it up right now. But that's the Milky Way galaxy you see there. Now, the Milky Way galaxy is actually a disk, and it's our perspective here that's making it look curved. And then these things down here, they're not fires. They're cities. We tend to think that, well, if you get out of the city, you're away from the light pollution. But you're not. You have to be a long ways away from a bright city before it stops causing visibility problems on the horizon and even straight overhead if you're looking at very faint objects. So you can get some idea of the light pollution problems here just by looking at this picture where you see those cities. So I thought this picture was pretty. I mean, that's, of course, why Microsoft curated it to show on my screen. But as far as astronomy goes, I thought it was very, very useful to point out some things.
Where's like one of the best places to look without
North Korea.
That's oddly really, yeah, that was specific.
Well, have you ever seen the pictures of the Earth at night?
Not near the borders.
Yes, not near the borders. And for safety measures, I wouldn't go close to where they detonated the nuclear bomb yesterday either. But if you've seen night pictures of North Korea, it's a black spot. You think it's the ocean. The middle of the ocean would, of course, be also a very dark spot. Yeah. Question?
What's the best place here?
The best place here. Well, University of Nebraska has their observatory in Meade, Nebraska, about 30 miles outside of the city of Lincoln. You can see the glow of Lincoln in one direction, the glow of Omaha in another, but they figured it was dark enough out there. So going with that, get at least 30 miles away from any city. And of course, there are only 2 cities, well, maybe 3 in Nebraska. So it's pretty easy to get away from the cities here. But, we will, for one of our labs, try to get out to, once again, Gary, can't remember his last name, to his house out in like Bennett, that's far enough out there that it's nice and dark. Okay, tides. We all know, well, maybe we don't. I grew up living next to the ocean, Monterey Bay Academy. Before that, in Liberia, pretty close to the beach. And so I've always had oceans as part of my life. So the tides and the waves and everything is always something I've known. Maybe not so for everybody. But we have roughly 2 high tides and 2 low tides per day. Roughly, it's not exactly 12 hours between them. And those tides, as a kid, you're out there and you notice the water level of the ocean is higher than it was and it's lower than it was, and that's all you think about it. I think that was proper English. But when you start studying physics, you start saying, now why? Why do we have these tides? And the reason we have the tides starts with gravity. But as your homework problem was pointing out, it's not the whole thing on gravity. The moon has a gravitational pull on the Earth. The Earth has a gravitational pull on the moon. The Earth is much more massive than the moon, so as far as we're concerned, the moon is orbiting us. And we can calculate the mass of the Earth by looking at the moon's orbit, because the moon's mass is insignificant compared to, well, it's not actually insignificant compared to the Earth's. The Earth orbiting around the sun, same idea. If you calculate the forces, which if you look at the homework solutions, how many people know where the homework solutions are? Okay, let me show you that. That way I'll also have the numbers. So this here was homework 3 that's coming up. Homework 2, of the ones I've graded, I actually have only graded the ones you turned on paper, just in case people were like, did you grade mine? What did I get? Only Gabby had the right question number 2, because I took 12.6 instead of 13.6 for number 2. And Gabby looked it up in the book and answered the right question. I started grading. I'm like, what in the world's this? Oops, she's right. I'm wrong. Okay, so the question at hand, right, what did I do? I just clicked on homework 2. Since it's already due, then I went in and put my solution there, the same place where you saw the questions to begin with. So I calculated here, and the strength of the force of gravity between the Earth and the sun is 3.54 times 10 to the 22nd newtons. It's a really strong force. Why isn't the Earth just plummeting into the sun? Anyone? No answers? Why is the moon not plummeting into the Earth? It's a really important question, one that Isaac Newton was contemplating. Remember my example with the ball rolling off the desk? Goes faster, it goes farther before it hits the ground. And the Earth being a sphere, if it's going fast enough, it can be pulled down toward the Earth, but it ends up doing a circle, going around circle with that circular velocity we calculated. And a couple problems here. It's the same thing for the Earth. This enormous force is not making the Earth fall into the sun because we're moving tangentially. That's what we call the motion in the circle. We're moving in a tangential direction, and we're constantly changing direction because of that force. But we don't get significantly closer or farther from the sun. Where we let go, we get a little closer and a little farther. So it's a really large force, about 200 times bigger than the force between the moon and the Earth. I said about 200, obviously. It's not exactly 200. I said more than, and it's actually less than. No, it's more than. It's more than. It's less than. 1.98 times 2. Well, yeah. would be 4.96 or 3.96. It's 3.54. So it's not 200 times. I was wrong in saying less than 200 times, but it's a lot stronger. So the sun is pulling on the earth a lot stronger than the moon is, but it's not the strength of the gravitational force that's causing the tides. It's the difference in the strength of the gravitational force on one side of the earth to the other side. So looking at my picture, the side that's closest to the moon here has a shorter distance than the side on the far side. And since the force of gravity, G m1 m2 over r squared, since it's over r squared, the side that's closer has a smaller number that's being divided by squared, which makes it even smaller. And so that has divided by a smaller number makes the force bigger. So the force per unit mass here is much bigger than the average force per mass on the Earth. Now notice I said force per mass. You take a little piece of water like this and you calculate how much force it has. And so the water on this side gets pulled away from the Earth because it's being pulled with a stronger force than the Earth is being pulled. But on the far side, it's got a smaller force. Notice this arrow is shorter. This is a shorter arrow. This is a longer arrow to indicate the strengths of the forces. So the Earth is being pulled away from the water on the opposite side from the moon. So the water is being pulled away from the Earth on one side, the Earth is being pulled away from the water on the other side, and you end up with the water bulging out on the side facing the moon because it's closest to the moon, and bulging out on the side opposite the moon because it's farthest from the moon. Now, let's go back to my calculations just so we can appreciate the numbers. If you calculate the force per kilogram on the side of the Earth that's closest to the moon compared to the side that's farthest, and do the same calculation for the sun, you see that you have a 1 times 10 to the minus 6 Newton difference. Now, 1 times 10 to the minus 6 newtons, that's a small amount, right? It's a pretty small amount. But it's a smaller amount for the sun by a factor of 2.2 than it is for the moon. So that means that the moon has about twice the effect on the tides, 2.2 times, because of that differential force. It's the difference in the strength of gravitational force from one side to the other. Now, a question for you to answer. I don't have a clear question on it. Why is it that the moon has a bigger differential force even though it's a much smaller mass? Because it's closer. Because it's closer, the diameter of the Earth is a much bigger fraction of its radius. The sun is so far away, the diameter of the Earth is a very small fraction of the radius. And so that's why the moon is the one that affects the tidal pull so much more. So I don't know what happened to, it's settings. Settings got screwed up again.
So the moon and the Earth are slowly separating, correct?
The moon and the Earth are slowly separating, and that is part of this. That comes from that. I'm going through that right now.
Okay. I was going to ask what effect does that have on this?
Okay, so yeah, if I forget, bring it back, because that is part of the tides. Notice it has the word centrifugal here. I just waxed, well, not poetic, just verbose on Facebook trying to explain the difference in centripetal and centrifugal force and inertia for a video of a guy doing a loop in an airplane pouring water. So when we say excess centrifugal force pushes water away from the moon on the far side, it's not, there's no such thing as centrifugal force. It's inertia. Trying to go in a straight line, it's not getting pulled as hard as the Earth, so it gets separated. Okay, now the sun has an effect. It's just less than half of the moon's. So if you have the sun and the moon all in a straight line, since you have a high tide both on the side closest and farthest, it doesn't matter if the moon and sun are on the opposite sides or the same side. You'll have your biggest possible high tides and low tides. What is the moon phase when you have a straight line with the moon, the Earth, and the sun? And notice I said it doesn't matter which side, so there are two answers to this. What's the moon phase when you have a straight line?
New full.
Either new or full. If it's a new moon, that means it's sun, moon, earth. If it's a full moon, that means it's sun, earth, moon. So new moons and full moons are going to be when you have your biggest tides. Your high tides are the largest. And first quarter and third quarter are when you have the smallest high tides. And these smallest high tides are called neap tides, whereas the largest high tides are called spring tides. And it's because both of them are affecting how big the tides are. Maybe this will come back. There is a third slide here. Well, let's not worry about the third slide. We'll just go to the animation. Maybe it'll come back. Maybe it won't. This is an animation from University of Nebraska's astronomy department to illustrate tides. Now, you can include the sun or not include the sun. So you see if I include the sun, it changes how big the tide is. And also shows you the phases for the moon. So here, with the sun way out to your right, you're having a new moon situation and you have the highest tides. I'm going to run this one time around without the sun at all, just showing the moon going around, the earth spinning, and you see the high tides are staying pointing at the moon. Of course, this is too slow for me to enjoy, so I'm going to now shift on the sun. Now with the sun is always trying to make high tides horizontally in our picture. And so here we're coming into the highest high tides. What do we call that? Spring tides. Now it's coming around, and spring tide was at full moon or new moon. That was a full. Now it's coming around, and you can see its water is more on the sides and not bulging as much. That's the neap tide. Well, let's do the last thing. Include effects of the Earth's rotation. Notice the Earth is rotating in this picture. If I have water and I have something underneath it that's moving, there is going to be a certain viscous force that pulls the water with the thing that's moving. In this case, we're going to call it tidal friction. The tidal friction is just that water is being pulled by the Earth as the Earth spins. And so because the Earth is spinning faster than the moon is going around, what do you think is going to happen to the position of the high tide when I turn on the rotational effect? It gets pulled forward. Did you see the shift? I'll turn it off and on. Well, not when it's at neap tide, because you won't see much if I do it at neap tide. So I'll turn it off and on so you can see how big the shift is here. So we have the high tides actually lead the moon by a little bit because of the Earth's rotation. Now comes the answer to the question that Aldwin asked. I have the Earth is, the mass is not symmetrically laid out here with the high and low tides. The Earth is acting like the closest part to the moon is out in front of the moon. And since it's out in front of the moon, this part is pulling the moon forward. So it's very much like when I take this and I swing it around my head. I can't make it keep going just by holding my hand still. I have to slowly pull forward with my hand. So my hand's doing a little bit of a circle, constantly pulling the bob forward. And that's what keeps it going. Well, that's what the high tide is doing to the moon. And so we're pulling the moon, but the moon, unlike this bob, doesn't have any air resistance trying to slow it down. And so the moon is just getting pulled, which makes it speed up. But when it speeds up, that makes it go to a higher orbit. So the moon is moving away from the Earth. I think it's something like a ½ inch a year or something in that ballpark, because of this tidal friction making the high tides ahead of where the moon is and then pulling the moon forward. Now, of course, if the Earth is pulling the moon forward, what's happening to the Earth's rotation? We have to be slowing down. We're giving up energy, we're slowing down. And so that means that the length of the day will be slowly getting longer because it'll take us more time to do a rotation. So over a course of millions and billions of years, this would have a significant effect on the length of the day.
So obviously we won't be alive for it, but will it eventually?
I'll be in heaven. I'll be observing, okay?
Okay, but will it eventually stop?
Will it eventually stop? It will asymptote to that. It will continually move out. And if time were to go long enough, I think we would actually lose the moon. But huge amounts of time. I've never done a calculation to make sure if we would lose it or not, but it seems like we should. But way off. What was that?
Didn't want you anyways, Moon.
I still didn't hear.
I said didn't want you anyways, Moon.
Yeah, you're just mean. Okay, that page never came up. I'm going to forget about it. This is the last one we had last class period, talking about the waves and specifically the wavelength on this slide. So remember, what's the name of this character? Lambda. That's a lowercase lambda.
What's up with this lambda?
Y'all watch Stargate?
Which one? The original one?
That's it.
That thing.
Okay. At least that's my recollection. We don't use uppercase lambda enough. I get gamma and lambda confused. Was I wrong, Gabby? Oh, I thought maybe you were correcting me.
Oh, so that's helpful.
Okay, we looked at this actually, so that was our last slide. This must have been looking at the range of electromagnetic waves. We're going to spend more time looking at the range of electromagnetic waves. Notice, once again, the visible spectrum is a tiny part. The visible spectrum goes from around 750 nanometers down to around 400 nanometers. And you have the colors in there. And you guys won't believe this. As a physics teacher, it wasn't until I became a physics teacher that I learned the order of the colors in the rainbow, right? In electronics class, I had to learn the color codes for the bands on the resistors. And a student said, "Oh, that's the order in the rainbow." I'm like, yeah. Okay, but now that I'm a teacher, I know these things cold because, you got to know something. And so you have that whole Roy G. Biv thing going on, right? Those are different wavelengths that go with the different colors.
We're not Arabic. We don't read that way.
We don't what?
We're not Arabic. We don't read that way.
Plenty of countries read that way. If you're Japanese, you can read any direction.
But that's because they go that. That's because it's funny.
Any direction. Okay, they don't go this way, but they go like this.
But that's also what Chinese is.
Anyway, that wasn't our goal here. Our goal is to learn about light. Now, I talked about the wavelength. Now let's talk about the relationship between frequency. This is the Greek letter. Anybody know the name for that Greek letter? It's nu. We usually just use an F instead. Nu stands for frequency. F stands for frequency and is a lot easier to remember. So the frequency of a wave, frequency is the number of times per second, multiplied by the wavelength, the distance for it to repeat, is the speed. It's actually very easy to come from that, or to come to that, because the frequency is equal to one cycle divided by the period. The period being the time to do one cycle. Remember, we talked about the Earth. What's the period for the Earth to do one orbit around the sun? That's the simplest way of saying it. The simplest way to say how long it takes for the Earth to do one orbit around the sun. 1 year. So we have a period of 1 year, so we can say the frequency of the Earth's orbit is one cycle per year. Or we could have said, one cycle per 365.2422 days. Or we could have broken it down. The standard unit for frequency is per second. So the standard unit is 1 hertz equals 1 cycle per second. So the electricity coming out of the wall is 60 hertz. That means it's going through 60 cycles per second. So the period, the time to do a cycle is easily found from that, or is the period. I can solve this for period and have period is equal to 1 cycle divided by the frequency. Now, period, the wavelength is the distance for 1 cycle. And so the wavelength should be equal to the speed at which it travels. C here is the speed of light in vacuum. Vacuum being a very odd word to write. I think that's right with 1 C and 2 U's. And so the distance it travels in 1 cycle is equal to the speed multiplied by the time for 1 cycle, which is the period. And since period is 1 over frequency, that's equal to the speed of light over the frequency. Therefore, the speed of light is equal to the frequency times the wavelength. Why do I go through all of this? So you can realize if you know any 2 of those 3 things, you automatically know the third. And for astronomy, we're always talking about light going through the near vacuum of space. So the speed of light for astronomy is always going to just be c. So you don't have to worry about, oh, it slowed down, went through water. That's really not an issue in astronomy. So we'll have, if you know the wavelength, you know the frequency because you know the speed of light. If you know the frequency, you know the wavelength because you know the speed of light. So you only need to know one. So looking at that, okay, I thought I had a better version of this. Looking at this, knowing what the wavelengths are, I can calculate the frequencies. For instance, if the wavelength is 750 nanometers, what color light has 750 nanometer wavelength? Red. Then the frequency is going to be the speed of light in vacuum divided by the wavelength. Speed of light in vacuum, it's an exact number. Here's the exact number. 299792458 meters per second. Exactly. That's been set as a constant. And if you do an experiment to try to refine the speed of light, you're actually refining the length of a meter. So that's the speed of light. For our purposes, we'll use 3 times 10 to the 8 meters per second. That's 300 million meters per second. I really wish that they would have just changed the meter by, remember the meter was supposed to be, well, a kilometer was 1/10,000th of the distance from the pole to the equator, but their surveying was wrong, so the meter was wrong to begin with, so why not just nudge it a little bit and make that number exactly. Yeah, hey, this is so close to 3, it wouldn't make a difference.
In vast distances, it will make a difference.
What does the prefix nano mean? It doesn't mean tiny. Means billionth, 1 times 10 to the minus 9. So 750 nanometers, 750 times 10 to the minus 9 meters. Now with this, I could do some math real quick in my head. 8 minus, because it's divided, 8 minus a negative 9 is 8 plus 9, which is 17. 3 divided by 750. You know, I don't know that off the top of my head. Anyone? Walk out here so I have enough light. 3 divided by 750. Of course, this thing also works horribly. I think that says 0.004. What do you say? You can't tell because of the lights that are out. So 0.004 times 10 to the 17th, and then for my units, Meters on top and meters on bottom canceled, so I have 1 over seconds. What's a simpler way of saying 1 over seconds? Good boy. I'm going to blame this on it being Friday. Hertz. So we have 0.004 times 10 to the 17th hertz. Well, how can I simplify that? That's not standard scientific notation. What do I need to do to get standard scientific notation?
Take away, you do like 4.0 times 10 to the 14th or something like that.
That's right. So I have to move it over 3. And so that's going to be 4.00 times 10 to the 14, exactly what Max said. And so knowing the wavelength for red light is 750 nanometers, I'm able to calculate that the frequency is 4 times 10 to the 14th hertz. Now that brings up another thing. Where is our vision ending? There's not a sharp cutoff. It's not like, oh, you can see 401 nanometers, and you can see 400 nanometers at 399 nanometers, no can see, right? It's not like that. It's your vision becomes less and less acute. And so you just kind of have to choose where you're going to make your cutoff. And what was that? Okay, so 400 is a really good spot, and 750 is a really good spot. Why? Because 750 gives you 4 times 10 to the 14th hertz for the frequency. So that means 400 is going to give you 7.5 times 10 to the 14th hertz for the frequency. So 400 nanometers to 750 nanometers is useful to remember, because then you can also remember that the frequencies are from 7.5 times 10 to the 14 down to 4 times 10 to the 14 hertz. Right? Basically the same numbers except for the exponents. So that's why we traditionally use those as our cutoffs, and not like, 367. I can definitely still see 367. It just be a little more difficult. Now our clicker question. I was trying to go for the Swedish colors today. I'm doing a lot of work on my Swedish ancestry. Channel 33 or session ID web ASTR. Jessica, this computer has your scores. In my office, it just drops them. I have no idea.
Yeah, I saw that and I was going to ask you, but I couldn't bring it in.
Norwegians don't like Swedish people.
The what?
Norwegians don't like Swedish people.
I am a quarter Swedish, an eighth Norwegian, an eighth Danish, quarter German.
So what, you like all the Scandinavian countries put together?
Yeah, pretty much. Except for my
The Finnish don't count.
my grandfather, he's the lone wolf.
What is he?
English.
Oh, so he's still there.
Okay, so we had 11 people with what I just said. 400 nanometers to 750 nanometers is the visible spectrum of light. Everything outside of it's still electromagnetic waves, but not visible. Now, I talked about the energy of light, and here we get to the equation for the energy. And remember, we more commonly just write F instead of nu there. The energy of a photon, a particle of light. Now, I went through last class period and talked about Thomas Young having an experiment that showed that light can't be a particle. Huzzah, everybody accepts that, they're good. Thomas Young disproved Isaac Newton, which is big, big time, right? But then in 1905, Albert Einstein writes his paper on the photoelectric effect. Now, a couple years earlier, Max Planck had suggested that if light behaved as a particle, what he meant by a particle was actually not what you and I think. When I say particle, I think of beam. That's exactly what I think. Well, that's not exactly what Max Planck said. He said if it comes with only specific amounts of energy, what we call quantized energy, just like we have quantized energy levels for electrons and atoms. If light comes in these quantized energy units, then Max Planck could explain the spectrum of light that comes off of something because it's hot, which we're going to talk about in just a minute. And then it was Albert Einstein who said, not only would that explain it, it's correct. And so Einstein said light behaves as a particle. But we already had an experiment that said it can't be a particle. Now that's kind of problematic. And so physicists have come up with what they call a complementarity principle that says light has two basic fundamental behaviors. It's a wave, but it's also a particle, but never the two at the same time. It's either one or the other. And so when you're treating light as a particle, you're treating it as a little packet of energy. And it has an energy that's a constant, Planck's constant, because he's the one that came up with the initial idea, multiplied by frequency. So you double the frequency, what do you do to the energy of a single particle of light? E is equal to hf. If you double F, what do you do to E?
You repeat the question, please.
Okay. The energy of a particle of light, what we call a photon, is hf. That's the equation for the energy, right? E equals hf. So if you double the frequency, what does that do to the energy of the photon? Increases it by how much? Doubles it. If we look at our visible spectrum, we go from 400 nanometers to 750 nanometers. Those are wavelengths, not frequencies. The first equation here, Planck's constant times c over lambda, is just using the relationship that relates frequency with wavelength. So let's stick with the frequency one. Instead of using 400 nanometers and 750 nanometers, we'll use 4 times 10 to the 14th hertz for red and 7.5 times 10 to the 14th hertz for blue. That's almost doubling the frequency, which means the particle of blue light has almost twice as much energy as the particle of red light. And if you go to higher frequencies, like ultraviolet, ultraviolet light has a very high frequency, and because it has a very high frequency, each little photon has a high energy. And therein lies the danger in electromagnetic radiation. Many of us walk around with cell phones in our pockets. I left mine in my office because I'm a good man, not going to be distracted by my phone during lecture. But your phone is using microwaves to communicate. Microwaves have frequencies that are much lower than the frequency of light. If you calculate the energy of a photon for a microwave, it's really quite low, which means that those microwaves, they can travel right through my body, but they're not going to really hurt me because they don't have enough energy to disrupt any of the chemical reactions going on in my body. Now, some people are worried that cell phones might be dangerous. After all, we have microwave stinking ovens. And we certainly wouldn't want to climb inside the microwave oven. Agreed? Now, you guys may or may not have seen it's like 7 years old. You guys, not being my age, 7 years was, you were young back then. But it used to be really popular for people to post videos on Facebook where they like take 4 phones and put them around a kernel of popcorn. And then they call the phones and the popcorn pops. Anyone seen that? Okay, it's bogus as can be. First of all, your phone is communicating with the towers, and so you don't have to have the phone ring for it to be sending out microwaves, although when you're talking, it's using more. But you can't cook anything with your cell phone. There's been a lot of research about the safety of cell phones. There has not been any conclusive evidence that there's a danger there. But since microwaves can cook food, it seems like it's something to look at. Microwaves actually cook food because, well, it was one of those accidental discoveries. Dude put his lunch on top of a microwave wave generator. It depends on what story you read.
The one I heard was he was working for Lithium,
Yes, that's correct.
and he walked in front of it and he had a chocolate bar.
No. He put his lunch bag on top of of the.
What's the lunch bag made of?
I don't know, but inside there was a chocolate bar, and the chocolate bar was partially melted. He's like, "What the heck?" And starts studying and discovered, yeah, you can melt stuff. You heat stuff up with the microwave, and what's going on is not breaking bonds, which is what we worry about. It's just making molecules vibrate. The frequency of the microwave is right to make water molecules vibrate. And of course, if these vibrate, they're moving faster. Moving faster, higher temperature, higher energy. And then, of course, you make the water molecules vibrate, and then that energy gets spread out, and you cook the food from the inside out. That's what a microwave does, right? You don't want to get in because you don't want to cook yourself from the inside out. Or your poodle like to keep making for crazy stories. I'm sure it's happened at some point. But short wavelengths, which means high frequencies, have very high energy photons. Those high energy photons have enough energy that they can actually break bonds, and that's bad. You break a bond in your DNA, who knows what's going to happen? Usually it'll just reconnect. But sometimes it reconnects wrong. And when it reconnects wrong, it usually dies. But sometimes it survives. And if it survives and starts rapidly reproducing, you have cancer. So you can cause cancer only by having energies that are UV or higher. That is light that is of higher frequency than ultraviolet. That's why we worry about, UVA and UVB. The cutoff between them is supposed to be where it's able to break bonds versus where it's not. Light comes in many colors. And this is where we start having fun. Because of time, we'll probably stop at the slides right here and just have fun. Yeah, woohoo! I don't know what it is, but it's got to be better than hearing him talk. These are just the coolest glasses that you can't keep. Don't write on them. Okay, so these here are what we call diffraction grating glasses. Now these are actually party glasses for little kids. But they have a bunch of little slits, both vertical and horizontal. And so if you look at things like, look at the light up above you, you see pretty colors, right? Here's one of the cool things to note. Look at a light across the classroom from you, and you should be able to see distinct colors. You should see a red color, a green color, a light bluish color, a darker blue color. Actually, there's yellow color as well. You see all of those? That's not what you would have expected, I hope. Those are the actual colors these put out. These don't put out all colors of the rainbow. They only put out specific colors. Why? Because inside you have mercury vapor that you excite. Just like I'm going to excite this in a few minutes. Go. Less than a minute, hope. That mercury vapor gives off ultraviolet light, high energy photons. And then they have the outside of the tube coated with powders that contain what we call phosphors that will absorb that ultraviolet light and give off specific colors because the electrons go up, absorbing energy, and then they fall down from here to here, or here to here, or here to here, giving you the different colors.
What kind of phosphorus is it?
I don't know.
Is it white phosphorus?
No, not that. That's a chemical element. It's a different thing, even though it's the same thing, at least as far as I know. So, Aldwin and Gabby, can you go back and close the blind so we can make it dark in here? There's actually two of them. One of them is dark and the other one's not. The dark one's, of course, the important one. Okay, so while they're doing that, I will turn out my lights. Thank you.
Thank you.
And we're going to look at some pretty things with our glasses. So first, we're going to look at what happens when I simply raise the temperature of something. So here I have a light, and right now I'm putting nothing through it. You see nothing, right? If I start to warm it up, now if you look at the filament, you see what color?
Red.
Okay, red, orange. And if you look off to the sides, you should see colors. What do you see off to the sides?
Still very much red.
you should see a little bit of rainbow action.
But come back to the door, like on the bottom.
I see the stuff from the door.
Now, that's a problem. But part of the rainbow is missing. What part of the rainbow is missing?
Looks like blue maybe?
Yeah, it's missing blue. Well, let's make it hotter. Now, what's the first thing you notice when I made it hotter?
I saw blue.
You see blue and,
Green.
well, yes, colors. It's something besides color.
A lot of colors became different.
It also became much brighter. So I make it hotter and you start getting blue and it gets brighter. The color is still orangish, but not as orange. Make it still hotter.
Still blue. I see purple now.
Now you see blue and some purple. You see the color has turned to a yellowish, almost white. And of course, it's much brighter. Get it even hotter. And now it's getting a reasonable facsimile of white. And you see plenty of blue and purple now. In fact, it's brightest now in the green to blue area, whereas before it was brightest in the red area. So what we see with this is called black body radiation. Black body because black bodies are the ideal absorber or emitter of light. It's also called incandescence. And that incandescence, you're giving off light simply because it's hot. And when you give off light because it's hot, you give off all colors, but the peak radiation depends on the temperature. And so we have Wien's law. I turn off projector already. We're not going to go back to slides. But Wien's law is an equation that actually relates the temperature to the peak wavelength, the wavelength that is the brightest, is the most intense. We also have the Stefan-Boltzmann law that tells us that the brightness, how much light it gives off, is proportional to the fourth power of the temperature. So if you double the temperature, 2 raised to the fourth power is 16 times. So doubling the temperature gives off 16 times more light. Why is this important in astronomy? Because this is how the sun puts off light. The sun is hot, and because it's hot, it gives off light, and it gives off a nice continuous range like this. But this is only one of 2 ways that we can give off light. So here's the other way. Turn this on and then turn the other off. This here is actually helium. It's a helium vapor lamp. So it's like a neon lamp, except for the gas is helium instead of neon. So if you look at this, now if you look at the center, you'd say that's kind of a peach color, right? But if you look out to the sides, what do you see? You see all kinds of lines there, right? But they're discrete lines. They're thin little lines. They're not continuous. And so that was a problem with the original model of the atom that Rutherford came up with, the planetary model. His model said that electrons can have any energy, which means electrons should be able to freely move, and you should have photons, these particles of light come out, with all different energies, all different colors. But we have only discrete ones. That's why Bohr, in his atomic model, said the electron levels can only have certain energy levels, and then the gaps between them correspond to the colors that we're seeing here. So this is the discrete spectrum. And as we talked about in last class period, when light is emitted, you only have these colors from the gas. When light is absorbed, you only have those colors absorbed. And if you change the kind of gas, whoops, they're right here. If you change the kind of gas, and this one, I think is a different kind of gas. We'll see. It is important to turn these off. One would not want to be electrocuted. Yes, this one here says hydrogen on it. You see it's a different color. See how it's all blurred? It's all blurred because it's no longer a vacuum inside. It's been damaged. That's the reason this one is sitting here, is because it's also been damaged and gives you all that blur. So it doesn't illustrate the point because it's contaminated. But a different gas will give you a different look. You can see the lines that are the hydrogen lines, the strong ones. but then all the rest is coming from contamination. So with light, this here is also important. When you look at the sun, you're not seeing emission lines from the sun, you're seeing absorption lines because the sun has gas outside of it. And that gas outside of it will then absorb the radiation that was given off from the sun because it was hot. And by analyzing the lines that we see, then we can determine what the sun is made of.